Hi, today we will discuss the time-dependent volume changes of concrete. Actually, there are three issues here: the shrinkage of the concrete, creep in concrete, and the thermal expansion or contraction of the concrete. For the creep and shrinkage, this is a time-dependent deformation of the concrete. Take note that concrete is elastic only under loads of short duration, and because of additional deformation with time, the effective behavior is an inelastic material. Under sustained loads within the plastic range that is below zero point 0.5 of Fc prime, concrete will continue to deform for a long periods of time due to creep or plastic flow. Inelastic deformation increases at a decreasing rate during the time of loading, and its magnitude may be several times as large as the short elastic or short time elastic deformation. Frequently, creep is associated with shrinkage since the two occur simultaneously and often provide the same effect, that is, increased deformation time. In the figure below, note that the general relationship of deformation versus time, the true elastic strain, decreases since the modulus of elasticity of the concrete is a function of Fc prime, which of course increases with time. So as you can see here, we have the true elastic strain from the bottom, and then if we apply shrinkage and creep, there will be nominal elastic strain. So you can see the strain increases due to shrinkage and creep. The internal mechanism of creep is that, or a plastic flow, may be due to any one or a combination of the following: crystalline flow in the aggregate, unhardened cement face, plastic flow of the cement face surrounding the aggregate, closing of internal voids, and the flow of water out of the cement gel due to external load and drying. There are factors affecting the magnitude of creep. Accordingly, the constituents such as the composition and fineness of the cement, the admixtures, the size, grading, and mineral content of the aggregates. Also proportions such as water content and the water cement ratio. Also the curing temperature and humidity. Relative humidity during period of use, age of loading, duration of loading, magnitude of stress, surface to volume ratio of the member, and slump. Of course, it's really difficult to compute or determine directly the creep for a concrete. So Branson actually made a general prediction method which gives a standard creep coefficient equation that is 4 inch or less slump, 40% relative humidity, moist cured unloading at 7 days or more. So here is the general prediction method developed by Branson. C sub T is equal to creep strain over the initial elastic strain, which is equal to T to the power zero point 0.6 over 10 plus T to the power zero point 0.6 times C sub U. Here C sub T is the creep coefficient at any time. Cu is the ultimate creep coefficient, which ranges from 1.3 to 4.15. However, Branson suggests using average of 2.35 under standard conditions. And T is the duration of loading in days. For a detailed calculation, you can look at book of width, pages 81 to 85 for a detailed calculation of creep. Here is the creep coefficient variation from 0 day up to around 600 days. As you can see, creep actually is quite high in the initial days, especially from 0 to 100 days. And then after 200 days, it slowly increases up to around the whole year. At 1 year, C sub T is around 0.78 of CU already. But after 5 years, it reaches around zero point 0.9 of CU. So as you can see, in long term, C sub T is increasing very slowly. Also, we have the effect of unloading. The effect of unloading may be seen from the figure below, where at a certain time, T sub 1, the load is removed. So if we have to remove the load, there is an immediate elastic recovery and a long time creep recovery, but a residual deformation will remain. Aside from that, we have the creep and steel reinforcement. What's the effect of the steel reinforcement with the creep? Creep of concrete will often cause an increase in the long-term deflection of members. Unlike concrete, steel is not susceptible to creep. So that's good. For this reason, steel reinforcement is often provided in the compression zone of beams to reduce their long-term flexion. So that's it. So steel reinforcement is very useful at the compression zone also because it will reduce the long-term deflection of the beam. Aside from the creep, there is the problem of shrinkage. Shrinkage is also a time-dependent deformation. Shrinkage, that is volume change, which is usually concerned decrease in volume during hardening and curing of the concrete. It is unrelated to load application. Unlike creep, it is related with the load application. So that's why creep and shrinkage are two different phenomenon. But normally, we only look at creep and shrinkage as one. But actually, it's not really the same. They are different. The main cause of shrinkage is the loss of water as the concrete dries and hardens. In general, the same factors have been found to influence shrinkage strain as those that influence creep, primarily those factors related to moisture loss. Also, the Branson developed a general prediction for shrinkage. Again, with the standard shrinkage strain equation, we use the standard condition that is 4 inches or less slump, 40% relative humidity, and minimum member dimension of 6 inches or less, and after 7 days, moist cure. The general prediction method by Branson is stated as epsilon is h is equal to T over 35 plus T times epsilon is h u, where T again is the time in days after moist curing, and epsilon is h is the unit shrinkage strain, and epsilon is h u is the ultimate shrinkage strain. The range is 400 to 1000 times 10 to the negative 6, but Branson suggests using 800 times 10 to the negative 6 for average conditions. Also, you can do some corrections relating to humidity, that is H. The correction factor can be 1.4 minus 0.1 H for humidity of 40% to 80%. But if your humidity is around 80 to 100, then your correction factor would be 3 minus 0.03 H. Again, for a detailed example calculations of shrinkage, I will refer you to pages 76 to 78 of WIT. There you can see how to compute the shrinkage of concrete. Here is the strain variation terms of shrinkage. Again, in the initial days, the shrinkage strain is quite large. At around 3 months, that's less than 100 days, your epsilon is H is already 72% of epsilon is HU. But after 1 year, it reaches around 0.91 of epsilon is HU. So here, as you can see, in the long term, the shrinkage slowly is waning. So as you can see, we have a very slow shrinking after 1 year. Shrinkage is very important for the first 1 year. How to minimize shrinkage? It is desirable to keep the amount of mixing water to a minimum. Also, if you cure the concrete well, place the concrete for walls, floors, and other large items in small sections. Place the concrete for walls, floors, and other large items in small sections to allow shrinkage to take place before the next section is placed. Use construction joints to control the position of cracks. That's what we usually do in road construction. We also have to use shrinkage reinforcements and use appropriate dense and non-porous aggregate. Actually, the aggregate content will really help to the limiting the shrinkage of your concrete mix. So as you can see, as we increase the aggregate content, the shrinkage ratio will go down. At around a portion with no aggregate, the shrinkage ratio is 1.0. But if we have to add 20% of aggregate, then your shrinkage ratio will be around 0.7. If we can add up to 60% of aggregate to the concrete mix, the shrinkage ratio will further decrease to 0.22. As you go around 90% of the aggregate content, or even 80%, your shrinkage ratio is around 0.07, 0.007 maybe. Okay, so there's really a good correlation with this one. By adding aggregate, the shrinkage of the concrete mix will really go down. Aside from the creep and shrinkage, there is also the problem with the thermal expansion. It's very important that you will know the coefficient of thermal expansion or contraction because this will affect concrete. Normally, for normal weight concretes made with siliceous aggregates, the expansion or the coefficient of thermal expansion alpha is 5 to 7 times 10 to the negative 6 strain per degree Fahrenheit. For normal weight concretes made from limestone or calcareous aggregates, that's 3.5 to 5 times 10 to the negative 6 strain per degree Fahrenheit. Also, for the approximate values for the lightweight concretes. That's 3.6 to 6.2 times 10 to the negative 6 strain per degree Fahrenheit. An all-around value of 3.056 times 10 to the negative 6 strain per degree Celsius may be used. Or also, you can use 3.33 times 10 to the negative 6 strain per degree Celsius for reinforcing steel, because as we have said, the coefficient of thermal expansion of concrete and steel are almost the same. So that's all for creep and shrinkage and the thermal expansion of concrete. Thank you for listening.